So we're going to follow up the discussion about how to implement synchronization with a short example of a special kind of synchronization called barrier synchronization. Here's an example of where barrier synchronization are really useful. So we have some number of threads, possibly going in and out of some critical regions on the way down to complete their task, performing some work, and some are running ahead of others and so on, because these threads, as we know, all have their own program counters and live their own life. So maybe some has been slowed down by exceptionally many cache misses, or maybe it was interrupted by handling I/O or something like that. But we can't expect all these threads to work exactly at the same pace all the time. So let's say that all these threads work together to update some kind of matrix in the scientific computing thing. So they do some matrix operation together, and before any of these threads is allowed to come into the next phase of the execution, where they start to make use of the data they produced in the previous phase, make use of that matrix, we have to make sure that all the computation of this phase has been completed. So we need to all the threads to sort of nobody can enter the yellow region here before we know that all threads have performed their task. And this is where we're going to use this barrier synchronization. So barrier synchronization is a kind of primitive, just like the lock and unlock. And this primitive is going to be executed by each thread right when they, at the end of this phase and before they enter the next phase. And it has the property that it waits until none of the threads will be allowed to get out of the barriers until all the other threads have also entered into this barrier. So you have to wait there and at that solid line there until you get into the yellow phase and start executing. Once more, there are a couple of ways you can implement this. We are going to discuss software algorithms in the next couple of slides. You could also potentially do this in hardware, and it has been done many times in hardware throughout history. And it's quite simple. You just let each processor has a little signal, and that signal goes into one big fat AND gate. Okay, and the output of that AND gate will be set if and only if all the CPUs have raised their little bit, input bit to the AND gate. This can be implemented with a physical gate, as I told you, but also it can be implemented by a special wire called a wired AND that behaves as if it was a one giant AND gate. It's very quick, very fast to react on this. The last CPU gets in there, sets its bit, and all the other CPUs will immediately see that everybody has arrived, because the output of that AND gate will go to 1. But it's not that practical to use, because you have to know exactly how many CPUs you're going to have in your algorithm, and you're going to have to allocate to exactly those CPUs. So it's not a very general solution, but it is a fast solution. So if you build some special hardware to implement some special algorithm, you may still use that. What we're going to use here instead is to look at software algorithms for implement barriers, and we will make friends of the lock primitives we designed in the previous set of slides. So here is a very primitive way of implementing a barrier. So this barrier has a barrier name, just as the critical section had some kind of were named associated with some kind of memory location. The barrier is also associated with some barrier name, and it turns out that this barrier name is actually a struct. It's not just a variable, as it was in the case of the synchronization. And we also specify how many processes or threads there are that we need to wait for at the barrier before we can go on and compute our task. We going to make use of the lock and unlock that we designed. So we make sure that so each thread will actually execute their own barrier, make their own call to this function. We'll make sure that only one thread at a time can be in between these two red statements and execute the blue code. So first, what we test is if one variable of that struct, which is the counter associated with the barrier, if that is equal to P, that means that we have to reinitialize the other part of the barrier struct, which is the counter part. We have to initialize that to a 0. If not, so this is just going to be done by one of the threads when you get to a barrier like that. Then you increment the counter, and then you get out of the critical region. And then you simply sit there and wait until the global counter, that's read and written by everybody, until it reaches the value P, because then you know that all other threads have also incremented that counter, and when it reaches P, you fall out of the barrier, life goes on. And then when you call this barrier once more, because the barrier could be inside a loop, for example. So next time you call the barrier, the first thread to get to the barrier will see that the barrier counter is equal to P, and it will reinitialize it to 0 again, and we can start to increment it. But we also know it's only the first thread that gets in here that will see that the barrier is equal to P, and it will reinitialize it. There is a problem with this implementation, though, and it's a major problem. So let's say that one of the threads, so all the threads with the P-1 threads are spinning here, happily spinning inside this while loop. They can spin, it's just a load operation, because so they can all spin in the local cache, not generating any traffic. That's all very good. And the last thread comes along and increments the value of the counter from P-1 to P. So everybody should be very happy. However, there could be some thread that is not paying attention. So maybe one processor is handling an interrupt, or have got a hiccup for some reason. You can't. There is no rule that says that your processor has to execute at full speed all the time. So there could be some reason for a thread to not see the fact that the counter reached the value P. So it's sort of behind, and it wakes up after some other thread has managed to get around the loop and get to the barrier again and have changed the value of the barrier. So that means that our poor thread that got behind will not see that that all the other threads got to the barrier, and we sort of start to lag behind everybody else. So that, of course, is not the property that we would like to get on these barriers. So what I'm showing here is a more realistic implementation of a barrier. So here you play a trick of having a local variable, local sense variable, that's local to just this thread, and that so each thread will set its local sense and toggle the local sense back and forth, just to make sure that it's not going to get out of sync with the rest of the other threads when you have this kind of reusing barrier. If one thread is quick to get out of it and out of the thread and will be able to reinitialize the counter value too quickly. Another feature you can see here is here also is that you can have some kind of timeout. So while you're waiting for everybody else to get to the barrier, you can have some counter counting in the background. This is not going to cost much. It's going to be your local variable, just counting how many loops you iterated, and if it gets above some unreasonable number, you may post some warning. So and I leave it to you to stare at that code instead of me explaining all those different lines.